To find the average acceleration. Acceleration equals the change in velocity divided by the change in time. We know this. I'll just have a look at my notes very quickly so I know I'm on the right track. I've just switched the air conditioning on. It is a little bit warm in here. Okay, so change in velocity. What's happening here? We've got a ball striking a wall. So a velocity vector here. The ball then strikes the wall, and then a moment later, they say, well, after impact here, the ball is turned around and is going in the opposite direction. And they represent that with an arrow towards the left, and they represent that mathematically with a minus sign in front of the 1.6. So it loses some energy there somewhere. Okay. So we can say is delta V, of course, equals V final minus V initial over delta T. So we'll do it this way. Okay, we'll just do it exactly like that. Minus 1.6 meters per second minus 2.0 meters per second divided by the time, change in time, 0.02 seconds. I'll put the 0 on there just like they have. Calculation comes out at minus 180 meters per second. Of course, it's an acceleration, so it is squared. That's not too hard. We're missing one piece of information, aren't we? The direction, because acceleration, of course, is a vector. And so what is that? What is the direction there? To the left. And what's the explanation? Why to the left? Who can explain to me, using some physics terms, why it's to the left there? Yes. Its initial velocity is to the right, and it's losing velocity to the left. Okay. So from that, from what you just said, what can we say that has happened in that time? Not necessarily in terms of velocity, but with something else. Think of Newton's second law. A force has been applied to the ball, hasn't it? And in what direction was that force? Well, what was the force caused by, firstly? The wall. The wall strikes the ball, you could say, in the wall's frame of reference. The wall might think, well, I'm walking towards the ball. Okay, if you think of it like that. The wall applies a force to the ball to the left, doesn't it? And therefore the acceleration, of course, is to the left. Yes, negative acceleration, absolutely. Not deceleration. No. In this case, it is negative acceleration. And so what we've said traditionally is that the ball goes at some speed v and slows down at this point. At one point, it's doing 0 meters per second, isn't it? It has no velocity. Yes. I beg. I don't. So the question is negatively accelerating to the right. Boys. Shh. It sounds like you're saying a double negative to me. Yeah. Think about it like this, boys. In which direction is the force on the ball because of the wall? It's to the left, isn't it? It's not. Oh, okay. I think. Yeah, I think you're taking it a couple of steps too far. If the force is to the left, you can say, okay, well, that's a negative force. But then you're saying, well, I don't need to say to the left. You can say negative or left. or you just say to the left or negative F? Think about it in the frame of reference of the ball of the wall. It's applying a force forwards. Uh, it's applying a force in newtons, which causes an acceleration on the ball. I better stop. Hang on, guys, because this will sound really terrible. Okay, we'll start again. Hang on. So the question was, because I put a negative sign there in front, and then I say to the left that that's like a double negative, and I'm saying, okay, I can understand that argument. I'm also saying that, okay, yes, the answer has come out by this calculation here is minus 180 meters per second, but I'm clarifying that that is an acceleration to the left. Not at all. In your text, it actually says, okay, therefore, that's 180 meters per second to the left. Oh, hang on, or away from the wall. Yep. Perpendicular to the wall. If the force is in, boys, please, thank you. If the force is to the left, the acceleration is therefore to the left also. Okay. I think, yeah, I feel like we were arguing about something that probably didn't matter all that much. Yeah. Okay, so anyway, moving on. The next question says, the average force acting on the ball during the impact. What is the average force? Well, we're going to go to Newton's second law, aren't we? Force equals mass times acceleration. And they give us the mass. The mass of the ball is 200 grams. We must change that to get our force in newtons. We must change that to kilograms. 0.2 kilograms multiplied by our acceleration, 180 meters per second. Force is, and I could continue on here if I didn't say, if I just left that as minus 180 meters per second. In an examination, a question in the examination, they're not necessarily going to know that you understand that that negative is to the left, so you would have to say that. Okay. So just by leaving it as that, it's not good enough in most circumstances. Okay, 0.2 times 180, 36.0 newtons. Is that okay, everyone? 36 newtons. And because force, of course, is a direction also, is a vector, it has a direction. And the question was the average force acting on the ball during the impact. So the force on the ball we know is to the left. To the left. It's also perpendicular to the wall. 3, you might say, 3 says average force exerted on the wall during impact, and we're going to have to say something like this by Newton's third law. Thank you. For every action, there is an equal and opposite reaction. The force is equal and opposite, equal in magnitude, opposite in direction. Perpendicular to the wall. And yes, and they clarify that at right angles to the wall. I expect nobody had any problems with that question there. Walking around the other day, actually with the other class, walking around the other day, they didn't have any problems at all. After that first example that we did, Newton's second law. As it relates to momentum. Now, this is a derivation that is you might need to do this in a test. I'm not suggesting. I never get it. I won't make hints about what's going to be in the test. If I mention test, it doesn't necessarily mean that it's going to be in the test. If I say this is likely to be in the test, it's probably going to be in the test. Newton's second law, force equals mass times acceleration. And we can break this acceleration down easily enough. Mass, acceleration, which is final velocity minus initial velocity, divided by, and I'll put it all over everything, delta t here. Stop me if you don't follow me. Okay, I'm going to break this up. Distributive law, is it? Is that what it's called? mvf minus mvi over delta t. What are we looking at here? We know this one. Momentum equals mass times velocity. Something has momentum if it has mass and velocity. It can't just have mass. Although if you think about it, and depending on the frame of reference in which you're talking, everything's moving really, isn't it? So everything has velocity, momentum, beg your pardon. And from this, if that, yeah, thank you. PF minus PI, okay, over delta T. And I won't use any more space down there, which is change in momentum over change in time. So that says the force as it relates to the momentum per unit time. Okay, we have another example here. Any questions about that? That's reasonably easy, isn't it? Finding average force from change of momentum. The first example that we did in this course, in this momentum course, was related to velocity. We did that that ball striking the wall at some angle. I think it was 40 degrees, and we were looking at the velocity of the ball. We're now going to look at the momentum of the ball. Okay. Finding average force from change of momentum. A car of mass 1,500 kilograms traveling at a speed of 16.0 meters per second east. Okay, so what are we picturing? I always like to draw a picture. Let's draw a vector diagram. Well, I use straight lines. They're painful, actually, I think, but I'll use them. Okay, traveling 16 meters per second east. So let's draw, I'm going to say that length is 16 meters per second. Takes 4 seconds to round a curve, which it does without loss of speed, and then heads south. So I'll take that point there, and I'm just going to, without loss of speed, is that what it says? Yes. So momentum, or the vector is going to be the same length, saying without loss of speed. So I've drawn 2 vectors. Make sure you do the arrows. Some people in the first test neglected to draw arrows in. So we'll label this vector as well, 16.0 meters per second, 16.0 meters per second. Have I done the right thing? East takes 4 seconds around a curve, which it does without loss of speed, and then heads south. Okay, and so what I've taken this from is this is north, east, south, west. What average force must act to turn the car? Of course, they're going to want us to use this, aren't they? Because we just arrived at change in momentum over change in time. What two pieces of information do we need to calculate this? Mass and velocity, don't we? We're given mass, we're given velocity, and we're given mass here. Okay, so we can change these 16 meters per second. I'm going to talk in momenta, plural of momentum. Somebody want to do that calculation for me? 1500 times 16.0, those SI units, that's okay. I've got it here. Okay. 24,000. Sec newtons, remember, is a unit for momentum. Newton seconds, they actually say it as sec newtons. Of course, this is the same. No loss of momentum. The other unit for this is kilograms meters per second. Is that right? Meters per second? Yes, it would be. So what's the resultant vector here? Well, change in momentum is equal to the final minus the initial, isn't it? And I better put the delta t there. We'll add that in later. This is initial. This is final. Minus the initial is going to be the reverse of that, isn't it? I'm going to flip it around and turn it around that way, and I'm going to add it to this vector here. Stay with me. Orange. For another straight line. Okay. Now what's that guy? That's minus the initial, isn't it? Equals, for consistency. It has a magnitude of 24,000 sec newtons. It is in the opposite direction. Now what's the resultant? What does that look like? Of the addition of F plus minus PI. Well, it's a vector. It goes down like this. I'll make sure you know in which direction it's traveling. Don't forget your arrows when drawing these diagrams. Now, what they're asking here is what average force must act? Well, we need to know delta P, don't we? We need to know the change in momentum. That's what that vector is called. What do we use? Absolutely. Easiest way. Your text will say you can draw scale diagrams. That's fine. They're totally legit. But I don't teach them. I think they're even harder. Scale diagrams are fiddly, and they're not very precise. Using Pythagoras, and I'm going to say that, Pythag. Change in momentum, that vector is equal to the square root of 24,000 squared plus 24,000 squared. Any objections? It doesn't matter. Okay, if you want to be picky, I can put the minus in there, of course. Yes, we're squaring it, so it'll come out in the wash there. Somebody do that calculation for me, please. 33941. 941 sec newtons. Does that sound reasonable? Well, it's our hypotenuse, isn't it? Yes, it's a little bit bigger than each of these. Yes, okay, that sounds reasonable. We haven't found our average force though. Running out of space. Sorry about if it's looking a bit messy. 33941 sec newtons divided by the change in time, which was 4 seconds. SI units are correct. It's not 4 minutes. You don't have to change the units. And will somebody do that calculation for me also? Newtons, thank you. Don't forget your units. And don't forget that force is a vector. It needs a direction as well. And we've drawn it. So that's southwest. We can say southwest because we were talking east and south before. I'll just put SW there. Momentum. Of course, I'm going to ask you to have a go at this, please. Just before I make this small, take note of the diagram. They're saying again, please. They're saying again, VI is U, VF is V, 40 degrees, 100 degrees. This is very similar to our first problem, example 1, I think it was. But it's different. Instead of finding the change in velocity, finding change in momentum. It's a lot easier than it seems. Okay, so I'll draw our vector arrows, and these were green, weren't they? Well, I'll draw my change in momentum, delta P. You need arrows for them to be vectors. What's this one called? U, V. What's this one? Negative U. It's U in the opposite direction. Oh, sorry, yeah, I'm using velocities, aren't I? Yep. You're going to have to because there's no PI. Yeah, what they've done here, sorry, they're saying this in velocity speak. I'm going to speak now in momentum speak. Thank you for pointing that out. This, of course, is minus the initial momentum. This was 40 degrees. So in here is 50 degrees. And I can divide this triangle up, make it a right angle triangle. Then we can use SOHCAHTOA to solve it. I know the magnitude of the final momentum. Let's do a quick calculation. PF equals, what does it equal? 50. 50, I'm going to use a different unit just to remind you. Okay, because remember, and how did I get those units? Remember, it equals mass times velocity. Mass is in kilograms, velocity is in meters per second. There it is there. Okay. So, question 1 says, change of momentum of the body during impact. That's the length of this vector here, delta P. Delta P equals PF minus PI. Momentum final minus momentum initial, which equals this plus minus this. We're going to do a vector addition in 2 dimensions. How do we work it out? I can't just do that. I've got to say, well, oh, sorry, were you going to say, Paul? Yeah, that's right, yeah. Let's divide this in two and just find the length of this delta P on 2. Okay. So cos adjacent over hypotenuse will give me something that I don't know, something that I do know. Cos theta. State the formula, please, people. State the formula you're going to use first. It's a good way to start. Cos 50 degrees. Adjacent, of course, is changing momentum on 2. Put it in brackets just to make it clear. We'll keep that by itself. Over the momentum final, which is 50 kilograms meters per second. That leaves us with delta P on 2 equals 50 cosine 50 by the text 32.14. Therefore, that delta P vector is equal to 64.28 sec newtons. It is a vector out from the wall. At 90 degrees to it. Next question, force that the wall exerts on the body. And we're just going through, we're repeating ourselves again. 2F, change in momentum over change in time. Change in time was 0.4 seconds. $160.7. Approximately, it says in the book, approximately. 160.7, what are we talking about? A force, so it's in newtons. Out from the wall. At 90 degrees. 3, of course, these questions are starting to get repetitive. The force of the ball on the wall by Newton's third. I'm shortening it and shortening it. Don't do this in a test. It's not. State it longer than that. Newton's third law. 160.7 newtons. Toward the wall. Perpendicular. Yes. The reason why I change the way I say things all the time is to show you that you can. Doesn't matter. As long as it explains to the person that's marking the test or the exam, whatever it is, that you understand that it's at 90 degrees or perpendicular to it. Okay? That you know that it's toward the wall or to the right. It's fine. We've only got 15 minutes. What was next? I wanted to do something else this lesson. I've got a video for. Did I show you the space shuttle video? No. It's a pretty good video. Pretty exciting.